Let's continue on looking at the action potential here. And we already did some of this. So talking about the different types of potentials. And we did kind of a brief overview of the neuron and where some of these potentials occur, as well as where some of the channels are located along the neuron. So now we're looking at two ideas about adding or combining different types of graded potentials. So we have temporal summation and spatial summation. So temporal summation is where we have a single stimulus that takes place at a single spot on the neuron, but they're slightly separated in time. So let's say we have a depolarizing event, and then maybe half a millisecond later, we have another depolarizing event. Because those two stimuli are so close in time, we can simply combine them. And as we can see the cases here, it's enough of a stimulus to get us to that threshold. Spatial summation, on the other hand, is where we've got stimuli happening on different spots, in different spots on the neuron, but they're happening at the exact same time. And once again, we can combine or add or sum those varying stimuli and determine whether or not we get to threshold again. In this scenario at the bottom, because one is a depolarizing event and the other is a hyperpolarizing event, then we actually get right back to rest, which is basically those two stimuli kind of canceling each other out. So summation is basically this idea of being able to collectively add stimuli together. If it's temporal, it's on the same spot to the exact same stimulus, but we have slightly different timing. So one stimulus, half a millisecond or so passes, another stimulus, and then we can add those. For spatial summation, it's different spots. So think about different stimuli coming in on that soma or that cell body. And because they're happening at the exact same time, we can also add them together. And the overall goal of summation is being able to qualify us to get closer to the threshold. So if we can sum a few stimuli that are slightly smaller, but they collectively are enough, then that will bring us even closer to that threshold value. Okay, so a quick checkpoint question here. Why are graded potentials unable to communicate over long distances? Ties into something we talked about as far as differentiating graded versus action potentials. So I'll give you a minute or so to think about this one and see what ideas come up. You can drop some responses in the chat as well. So why are graded potentials unable to communicate over long distances? Okay, everyone's super quiet. No one has ideas. Oh, here we go. I've got some ideas here. They aren't able to meet the threshold value. Okay, yep, that's one part of it. Small deviation from the resting membrane potential, that is also true. Someone else is saying that they dissipate, which is excellent. The magnitude decays as the graded potential spreads, that is also true. And then I'm also seeing because its magnitude decays as it spreads. So yes, that is absolutely correct. So the way that I kind of like to think of it is think about a water hose. You've got water flowing through that hose. And that's kind of the way that electrotonic conduction happens, where we've got that negative positive energy that's creating this longitudinal currency down the length of that tube or hose. Now, as far as graded potentials, think about there being small holes along the length of that water hose. And so as water is moving from point A to point B, we're kind of losing the intensity. And that's what happens with graded potentials, where as it travels further along the neuron, it just kind of sizzles out or fizzles out or dissipates as it moves from one point to the other. So they are not able to be sustained as long as graded potentials are. Okay, great. Objective 2, we're going to talk about the ionic basis of an action potential. So what's really happening, what ions are moving in what direction. And then we're going to talk about the gating mechanisms for the voltage gated sodium channels and the potassium channels. So as we talk about the action potential, we want to look at some different directions of change of the membrane potential from that resting, which is -70. So the resting is kind of a reference point. And then we can talk about different types of events that will change or alter the membrane potential, depending on what's actually happening at the ionic base, on an ionic basis in terms of what ions are moving. So we've got depolarization, and that's essentially upward or positive changes of the membrane potential. And we talked about the fact that sodium is most likely moving here because sodium has an inward current into the cell. And so that will make the membrane potential be more positive as it tries to approach the equilibrium potential for sodium. We've also got repolarization, which is the opposite movement. So this is where the membrane potential is moving closer to rest. It's becoming more negative. And we also pointed out that potassium is likely moving here because, again, potassium's ECDF is out of the cell. And because it's positively charged, this type of movement makes the membrane potential more negative. And that is what gives us this downward stroke as potassium is trying to get closer to its equilibrium potential, which is on the far other end of the spectrum. And then we've got hyperpolarization, which is simply a negative membrane potential change that is beyond the resting membrane potential. So if the membrane potential becomes even more negative than -70, that can be considered a hyperpolarizing event or a hyperpolarization. So these are the different directions of change from the resting membrane potential that are caused by different movement of different ions in different directions. And we'll talk about what those ions are, but we already know that positive changes are going to be caused by sodium, negative changes are going to be caused by potassium. As far as the various ion channels throughout the neuron, we kind of touched on this on Monday. We've got leak channels that are always open. They're kind of contributing to the resting membrane potential. They're found throughout the neuron generally, but a little bit more concentrated along the axon. We've got ligand-gated channels that can be opened or closed depending on whether or not they have something bound to them, a ligand binding on to them. These are located on the dendrites as well as the soma or the cell body. We've got voltage-gated channels. These are sensitive to changes in the membrane potential. So they're going to open or close depending on what the value, what the membrane potential value looks like. If it's positive, some channels are going to do some things. If it's negative, other channels are going to do other things. So they're going to be voltage sensitive. And these are going to be the sodium and potassium channels that we're going to speak about here shortly. These are found throughout the neuron again, but slightly more concentrated along the axon, even more so at the axon hillock, sort of that neck region of the neuron. And these contribute significantly to the action potential. And then finally, we've got calcium channels. These are located only on the axon terminal, so the very end of the axon, that bulb, which we call the axon terminal. And these are responsible for releasing neurotransmitters. So neurotransmitters are essentially chemical signals or chemical signaling molecules that are released at the end of the neuron, and they will cross that synaptic, that area of communication and communicate to the neighboring neuron. So this is where electrical energy is converted to chemical energy, and then it can be reconverted to electrical energy on the neighboring neuron. And we'll talk more about some examples of that. Let's look at the gating mechanisms as far as the channels are concerned. So let's first talk about the actual channels that are involved here. So for for potassium, we've got leak channels we know about. We talked about those before. They're always open. They're contributing to the resting membrane potential. We've also got voltage gated channels, which open at a particular membrane potential and then close when that gets back to rest. So potassium is going to be slightly more straightforward in that it only has, as far as the voltage gated channels, there's only one mechanism for opening and closing that channel. And I'll explain more about what that means coming up here. Sodium now has mainly voltage gated channels. We know that there are leak channels, but there are much fewer than potassium, right? The membrane is much more permeable to potassium. But the sodium voltage gated channels are slightly more complicated. Now I'll explain what that means. And they're going to be more important as far as initiating that action potential. So we've got mainly voltage gated channels, few leak channels, and these voltage gated channels are slightly more complex and they're more important to initiating the action potential. And we know, just to kind of zoom out here and just make sure that we're understanding this correctly, when we talk about the membrane potential changing, all that's happening are some channels are opening, some channels are closing. And so because those different channels open or close, then we have more or less movement of specific ions, and that's what actually brings about the membrane potential change. So if I close voltage gated sodium channels, then sodium can't enter the cell and I can't have a depolarizing event. So when we're mentioning changes in the membrane potential, in your mind, you should simply be connecting that to opening versus closing of some channels versus others. So let's look at sodium voltage gated channels here. As I mentioned earlier, they're slightly more complex because they've actually got two gating mechanisms on that channel itself. These channels are going to open at -55 millivolts. So -55 is our threshold value. I kept mentioning that word threshold. The actual value is -55. And so when the membrane potential gets to -55, which happens because of those smaller graded potentials, then that triggers the opening up of these voltage gated sodium channels. And that's what we mean by these channels being voltage gated or voltage sensitive. They're going to do a different thing at a different voltage. When this happens, sodium rushes into the cell because that's the direction of its ECDF into the cell. And the membrane potential rapidly increases towards sodium's equilibrium potential, which we know is very positive at +60, but it never quite gets to that +60. It's going to be deactivated as soon as it hits +30. Again, indicating the fact that this channel is sensitive to different voltages. So at -55, it opens, but at +30, it closes, okay? Let's look at the two gates that are associated with this channel. So we've got an activation gate kind of at the top here. And then we've got an inactivation gate, which is kind of a second barrier or kind of a security, secondary security gate for this channel as well. And so the activation gate is voltage dependent only. It's going to open at threshold at that -55. Sodium is going to begin to rush into the cell according to that strong ECDF. And that will create a depolarizing event, that upward shoot of the membrane potential. Now, because this is a positive feedback mechanism, again, bringing us back to that, that mechanism of potentiating or augmenting a specific response for a desired period of time, this is an example of that positive feedback mechanism. So if we open one sodium channel, sodium rushes into the cell, the membrane becomes more positive, so that further triggers other voltage-gated sodium channels to now begin opening up, and that allows more sodium to rush in, and so on and so on. And that's what's responsible for that quickness of the rise of the membrane potential, is that it's a positive feedback event that's just becoming stronger as more of those channels open up. The inactivation gate, on the other hand, is both voltage and time dependent. So there's a timed component to the inactivation gate or that secondary gate. It's going to open during depolarization, but then there's going to be a 1 millisecond signal to have it close after that time has passed. And so it's going to also close during depolarization. Okay, so I'll say that again here. So because it's both voltage and time dependent, it's sensitive to the voltage, but then it's also sensitive to a timed event here as well. So it's going to open during depolarization, and then there's a 1 millisecond delay where it's going to close again after that 1 millisecond has passed. Okay, before we actually kind of illustrate this here a bit, let's look at this schematic diagram or drawing on the right. So we've got the channel itself, we've got the activation gate, we've got the inactivation gate. Now, this is what the channel looks like at rest. So at -70, the activation gate is closed, so there's no movement of sodium, but the inactivation gate is open. And so in this state, we say that the channel is closed, but it's capable of being opened if the right membrane potential comes about, if the membrane potential gets to threshold. Let's say the membrane potential does get to threshold. We start having that depolarization event as the activation gates open up. So the activation gates are now open, but remember that second gate, the inactivation gate, now was instructed upon that -55 condition. There was a second instruction that was put in place that this inactivation gate should open now, but should close after 1 millisecond. And so that allows sodium to rush in for that 1 millisecond, but then the inactivation gate closes. And so after 1 millisecond, the channel is now closed and incapable of being open, because as long as the inactivation gate is closed, there's no opening up this channel, no matter what the membrane potential looks like, okay? So even if we had another threshold stimulus, we still would not open this channel because it's closed and incapable of being open. And it's going to remain this way until we get back to rest. And at rest, we're going to open up the inactivation gate once again and close the activation gate again in preparation for a second stimulus.